Hello everybody. Pretty excited today as I got a new set of earphones and microphones. So I heard from a lot of people that um, the lectures made on audio are almost visible. Audible only to one earpiece if you have an earphones. And I got a new set. I hope I'm audible well enough today. All right, perfect. Recently, I got a comment on one of our videos. I think it was a common drain amplifiers where we derive the equation for gain. And when I was making the lecture, I took this fact pretty for granted, but then when I got that comment, I understood that it's not as straightforward. So the comment asked as to why the viewer posted in a comment as to why delta or dou VTH over dou V in was equal to eta times dou V out over dou V in. I'm very bad with my Greek alphabet, so forgive me if I don't pronounce this correctly or if I'm totally wrong, right? So it might be delta or del or dou, whatever I might call it, but you know what it means, right? So partial differential, that's all. So he posted a comment as to why this is true. So I first thought of replying in the comment, but then I realized that it's a whole big derivation to show as to why this is true. But don't worry, it's not boring. So we'll get through it pretty soon. Okay. All right. First of all, this was applied for the video where I derived the gain for the common drain amplifier. So let me draw that first. We have V out there and an RS here, and this is V in and VDD. So, and we know that this is the bulk, right? Okay. So first of all, we know we have the general current equation. So a bit of facts I talk about today might seem redundant, but just bear with me. Mu n C ox W over L VGS minus VTH the whole square, right? Okay. So what is the definition for transconductance? Even before I write it, you should know it. So GM equals change in drain current for the change in gate source voltage, right? This is a very typical definition from the and it's also explained in the transconductance lecture. So I'm doing it again here. So if we have to derive for GM, let's differentiate, let's call this equation 1. So if we differentiate equation 1 with respect to VGS, what we get is GM equals half times mu n C ox W over L 2 VGS minus VTH, right? And times 1. So 2 cancel. I'm not explaining it, it's just I've done it before in the transconductance lecture. So mu n C ox W over L VGS minus VTH, right? This is GM. Okay. Now, when we consider body effect, right? We say it's GMB, and I know I've not done this before, the GMB part. So if GM, let's go up here and see. If GM equals the change in drain current for the change in gate source voltage, what should this be? It's pretty intuitive. So the same change in drain current to the change in what? Right? The bulk to source voltage. Right? That's all it is. So that's the body effect, right? So if we differentiate equation 1 again with respect to VBS, right? Let's see what we get. GMB equals half mu n C ox W over L. I hope you're working with me on paper so that I don't have to keep scrolling up to show what I'm doing. Times 2 VGS minus VTH times, and listen up here. What happened here when we were doing it for GM was that VTH is constant and VGS is what changes, right? So, with respect to VGS, and that place VTH is considered constant. But when we consider body effect, there is a change in VTH, right? So we cannot ignore the differential of that. So that is where we get minus delta VTH over delta VBS. Yes, correct. That's correct. Okay, so again, 2 cancel, and what we have left here is mu n C ox W over L VGS minus VTH times yeah, the same thing. And this here is nothing but GM, right? We've derived that here. So it's GM times negative this. Okay? Alright. And I've said it in a few lectures that GMB equals eta times GM, right? So that's all eta is, right? This is all. So just to remove the negative sign from here so that we're not troubled a lot, what we do is we change the polarity of this voltage here, right? So what we do is just write VSB to remove the negative sign from there. So GM times del VTH over del VSB, right? Okay. Oops. All right. Let me take a different color, okay? And we'll discuss what this is. So first of all, VTH, if you... Ooh, that's too dark. So VTH is a very simple thing. VTH naught, that's like the basic threshold voltage, like without considering body effect. So this VTH is considering body effect, right? So it's given by a really weird looking equation. Okay? And I think this is called phi or phi, I'm not sure. But it's called PHI, so whatever you want to pronounce that as. So minus root of 2 times phi f. Now don't ask me to explain this equation, it's really weird, and generally, you know what, we don't use this much in circuit design, so it's kind of not very important, but basically this is of course self-explanatory as to what VSB is, and gamma here, this one, is the body effect coefficient, and that itself is a whole big thing, so don't worry about that. And the phi is, I think it's the work function of the doping in the substrate, right? Phi, I think, is given by kT over Q natural log of N sub over Ni, right? The intrinsic doping, and this is the doping in the substrate, and K is the Boltzmann constant, Q is the charge on the electron, and all that. So that's all totally solid state electronics, and it kind of freaks me out when I when I talk about solid state, because it's really confusing to me. But for circuit design, we're not going to be using much of that, right? But all we have to know is it's a constant, because we're going to differentiate this. We have to know it's a constant. That's all. All right. So even this is constant. So why don't we differentiate this equation with respect to VSB, right? So here we go. Delta VTH over delta VSB. Is this goes to 0, it's constant. So what we have here, and if you open this parentheses, you'll have a gamma times 2 pi f, right? I mean 2 phi f. So that whole thing is again a constant, so it's gone again. All we have is this term, and if you differentiate that, what do you get? Gamma times half, this is power half, right? So a half and 2 phi f plus VSB power minus half, right? So this can be written as gamma over 2 root of phi f plus VSB, right? Del VTH over del VSB, right? Now, this weird looking thing is nothing but eta, okay? Del VTH over del VSB. Just for our convenience, we call it eta, okay? So, alright, sorry about that interruption there. So this is what we got as GM equals, GMB equals GM times dou VTH over dou VSB, right? So this is now eta, so GMB equals eta times GM. Now, for this lecture, it's very important that we understand this part, right? Now that it's understood, let's apply that to the common drain amplifier case where we're deriving for the gain. So, let's draw that thing again. V out, V in, and this is VDD, and this is the bulk connected to the ground, right? And this is RS. So I mentioned in that lecture that delta VTH over delta Vin equals eta times delta V out over delta Vin. First of all, if we take this, what we get, oops, we're out of paper, so let me go there. Okay. So delta V, if we apply the chain rule, what we get is this: delta VTH over delta V out times delta V out over delta V in, right? So I'm saying that this is now equal to eta. And how can you say that it is equal to eta? We just derived that delta VTH over delta VSB equals eta. For this structure, the common drain, VSB is what? This is the source and this is the bulk, right? So VS minus VB equals V out minus 0. So it's just V out, right? So this can be said as equal to delta VTH over delta V out, right? Hence, delta VTH over delta V in can be written as eta times delta V out over delta V in. Perfect. I hope this clarifies the doubt about this one, and thank you very much for pointing that out. I just took it for granted, so this was really good. Thank you so much. See you later.